This program is a presentation of UCTV for educational and non-commercial use only.
I think that one of the things that we can take away from Roger Revelle's just tremendous inspiration and leadership is that great scientists work on great problems and have the vision to understand what those problems are before the rest of us do. And I think a hallmark of Roger Revelle's work was his ability to do that and then bring into the fold other scientists who caught pictures of the vision, and then they understood how they could contribute and fit into the big picture, whether or not it was looking at the oceans or the interaction with geology and the air, or whether or not it was to even found a university. And so it's the problems that you have the vision to work on that I think really distinguish the great scientists from all of the rest of people like myself, and we owe a lot to Roger Revelle for setting a tremendous example. I'm going to tell you about a great problem, about probably today's greatest problem in science. And therefore, I would say that we need that vision and leadership in order to address this problem. And I'll make the case that not only is it today's great problem, but because of a conspiracy of nature, that it's a problem that can't wait, because if we don't cure cancer in 20 years, tragic as it is, the world will stay the same. It may not be better. If we don't build the next computer faster, better, cheaper, the world will be the same. But if we don't cure, fix, or somehow deal with this problem, the energy and climate problem, then the world simply won't ever be the same. So we have to understand that that is what is before us and why this is the problem of our time. I'm going to tell you about the scale of energy, because climate is really not just observing the facts of the evolution of our planet and its systems, but of human impact on it, and that comes to the forefront in energy consumption more than anywhere else. But you can't fix a problem unless you understand its scale. So I will tell you briefly about the real scale of energy, and then tell you what the problem really is and how large it is, so that we can come to grips with what it will take to actually deal with it. And then I'll tell you about the options that nature gives us on the table, as opposed to what politicians would like to give us on our platter, for what really the allowed solutions are to a problem of this scale. If you want more details or a longer version of this talk, you can go to my website, which is just my initials at caltech.edu, where you can get a transcript and a video of a public talk I give on this topic and much other information as well. I'm not the only one saying this. Rick Smalley, Nobel laureate, inventor of carbon buckyballs and nanotubes, nanotechnology, testified in Congress that energy was the most important challenge facing humanity today. Our trade journal is saying it. The pundits, like my now friend Tom Friedman, is saying it. Presidents of universities are saying it. If we thought this was under control, we would be doing other great problems. And yet I say we collectively, because every major university in our country has now recently established centers, institutes, and infrastructure to deal with the energy and sustainability issue. And that's because we understand that it is not just the case that we have all the technology, we just need political will. We need more than that. We need the political will as well as fundamental advances in science and technology in order to enable a clean energy future in the time we have to get it online. Here are the units of energy in unintelligible units like barrels of oil equivalent and short tons of coal and kilowatt hours of electricity. In the only units I think people can really understand, watts of energy consumption. A laptop is a few watts. 1,000 laptops is a toaster, a kilowatt. Don't leave your toaster on very long. It's your average total home electricity load is a kilowatt. It's more than my big screen TV, so I win when I fight with my wife that it's her hair dryer really that's the problem, not my plasma. 1,000 watts, a kilowatt, 1,000 of them, 1,000 flying toasters is a small jet engine. It's a megawatt. 1,000 megawatts is a typically sized output of a nuclear power plant like the two you see up the road at San Onofre. It's a gigawatt. And 1,000 nuclear power plants is a terawatt, a trillion watts, and that's the average electricity demand of the world. You know, I have to explain to some audiences, but I'm sure not this one, that this picture wasn't all taken at once. You get it. Nevertheless, you can see the 2 billion people that live for under $1 a day and don't have modern energy or electricity. You can see the difference between North Korea and South Korea above the 38th parallel. And you can see all sorts of other geopolitical and important regional debates that I won't go into more here today, but I do want to use this to remind you that even this 1 trillion watts of energy consumption is high-value energy as electricity and is only a fraction of the energy the world consumes. When you add up all the primary heat content of the energy the world consumes and divide it by the number of seconds in a year, you can get the average total energy consumption rate. And we need another factor of 10 to see that. It's 13 trillion watts. In fact, that was in 2001. Last year it was well over 14 trillion watts. So that's the scale of energy if you want to solve a problem you have to deal with, not getting a few cars off the road and saving a few light bulbs in Fresno. The United States consumes 96 quadrillion British thermal units in a year, another great unit you'll read in our National Energy Policy Report, but I guarantee you it's an average energy consumption rate of 3.2 terawatts. Of course, 85% of it is nature's fuel over the millennia, oil, coal, and gas. A little bit is hydro. Biomass is still almost 10% of our energy consumed, but don't be fooled. This is unsustainably burnt, where we're decropping and deforesting at a rate much more rapidly than it can be sustained. The amount of sustainable biofuels and biomass, even from wood, is in the total renewables column at 0.2 of a terawatt. And then there's nuclear power, which is 0.9. That's a significant chunk of our total. Now, the astute amongst you will immediately know that we only make 0.3 terawatts of electricity, but this is the heat content produced by nuclear fission in those nuclear power plants, only 1/3 of which produces electricity, in the same way that this is the heat content of burning all the coal, of which only 1/3 produces electricity. That's secondary energy. This is the primary energy content on a fair footing of all the energy consumed on our planet in a recent year. Now, we can say that maybe if we value energy security and national security, that this will change as we start to run out of oil, coal, and gas. And the market forces will naturally just lead to a price differential that will make us all tend to go to more renewable sources. But quick math shows you that's not the case. If you add up the proven reserves and divide by consumption in a recent year, for which there is good data, you see we have between 40 and 80 years globally of oil, between 60 and 160 years of natural gas, and almost 200 years of coal. as proven reserves, both in the United States, in this case, and globally. Some people look at this and say, that means we're going to run out of oil in 40 years. But the ratio of proven reserves to consumption of oil has been 40 years for the past 100 years, since the day after oil was discovered. The reason for that is when it costs you $1 million a day, even today, to drill a well in the Gulf of Mexico and still only 1 in every 4 hit oil and the other 3 are dry, you adjust your exploration budget to prove out 40 years worth of reserves. It doesn't pay to prove out 100 years of reserves and leave it in the ground. And so we always have about 40 years worth of reserves at any point in time. What matters more is the resource base, which the USGS estimates there is to be had by humans on our planet. We have between 50 and 150 years of oil, between 200 and 600 years of natural gas, and almost 2,000 years of coal. Furthermore, if we start to peak in oil, we already know how to make gas and coal into oil. Germany did that in World War II. When denied oil by the Allies, they ran their country on a dime by converting coal into liquids. South Africa does that today when boycotted by apartheid. They run their country off of, in part, coal made into liquids when it was boycotted externally. It also happens that that plant is the single largest point source of CO2 on our planet, visible from outer space. But when CO2 is free, we can't be bothered with little things like that. Since we know how to make one form into another, and we have ample resource base, this is going to be the cheap way to get our energy for a very long period of time. And this does not count the methane clathrates off the continental shelves, of which there is estimated to be more than all the oil, coal, and gas on our planet combined. So from a point of view of fossil resource base, the way I like to tell people this is the Stone Age didn't end because we ran out of stones. And the fossil energy age is not going to end anytime soon because we're going to run out of fossil energy. But you have to be careful what you wish for. You might get it. We might burn even a significant fraction of all of that fossil energy. And that might lead us to something that I'm sure you are all familiar with by now, is elevated levels of CO2 in our air, because we may run out of oil someday, but we've already run out of air in which to put all its combustion products. And that's the great problem we have to deal with. This is an important paper by Marty Hoffert, now a colleague of mine that I work with, published in Nature. It summarized a scenario called Business as Usual from the Intergovernmental Panel on Climate Change's 1992 report. And this paper is not about climate, it's all about energy. And I want to lead you through that so that you understand what was embedded in the business as usual scenario to show you how challenging the real problems actually are. Well, in order to understand energy consumption, you need to understand people, since people consume energy. Here's the last century. Here's what they predicted the next half century will bring. And my favorite out year for this is 2050 for 2 reasons. One, I am privileged to teach 18-year-olds at Caltech. I've taught every freshman entering our college for the past 22 years, and I love it seeing those fresh faces who definitely want to know what our planet will be like when they're now my age. The second point is that energy is not like Google. You can't set up something and 2 years later in a garage be $1 billion company. You have to make a lot of stuff. And when you build a nuclear power plant or a wind farm, it's up there for 40 years. And that means that the energy infrastructure in 2050 on our planet is not 41 years away from us now in 2009. It's at most 10 years away. So this is not the next generation's problem. This is our problem to deal with now. Well, you can pick your favorite number. We're at 6 billion people, projected by 2050 to be 9 or 10 billion. Call it around numbers 10. It won't matter. Then we have to understand GDP growth. because we wouldn't consume much energy if we all lived in caves, if we didn't come to work today or didn't put on the lights, and energy consumption does track productivity. And the IPCC, under business as usual, projected that the historical average of global GDP growth would maintain itself for the next 50 years. That number was 1.6% per year. Now, in 1992, nobody foresaw the sustained double-digit growth of China and India. The developed countries claim that 3 or 4% economic growth is a target for sustainability. As we painfully see today, no country has a policy against economic growth. So it's unlikely this number will go negative, we hope, for very long. And you can argue this is conservative, but if it's 2 or 3 or 4%, the situation will just get worse. So we'll pick a conservative number here as a guideline. These two factors, population growth and economic growth, through the magic of compound exponentials, would lead unmitigated to a tripling of energy demand within our lifetime, to on the order of 45 trillion watts. But we mitigate that, because we save energy per unit of productivity, since energy does cost money. And we've been saving energy at the historical rate of 1% per year. Now, the United States actually is saving energy about twice the global average, and that's only because we are so wasteful that it's easier for us to save energy than when you only have one candle at night. You can't save in an absolute sense very much. And since the developing countries are growing, they're not saving, and the developed world is saving about 2% per year for this average of 1. But if it were 2 or 3%, nothing I'll tell you about will change. This will not be easy. To maintain this 1 or even 2% per year for the next 40 years will require tremendous advances in energy efficiency, because through the magic of compound exponentials again, this projects an average energy consumption per person on our planet within our lifetimes of 2 kilowatts, this horizontal line. The United States' current energy consumption is up here at 10 thermal kilowatts per person. This is 5 times less than the current per capita energy consumption of the United States, is embedded in business as usual in that IPCC scenario. To understand what 5 times less means, if you drove your car an hour today total, you couldn't eat, you couldn't have any electricity, you couldn't heat your house. That would be your total energy budget. The most advanced energy efficient countries, Japan and Switzerland, are above this line. China is now above this line. India has a government policy to bring its citizens out of poverty and get above this line within 10 years. But we'll assume, according to business as usual, that starting today we follow that energy efficiency trajectory and reach this point. Now, to give you a feeling for how energy efficient this is, humans are 100-watt light bulbs. A 2,000 food calorie a day diet is the equivalent of 100 watts average consumption. On the other hand, the energy embedded in food, the energy needed to grow the food, to farm the food, to move the food into the supermarket, to get it to your refrigerator, is between 10 and 25 times the energy in the food itself. If we can hold it to 10, then 100 watts per person burdens the system with a kilowatt, and I'm going to give you 2. So we'll give you twice as much energy as it takes to eat in a developed society as the world average energy consumption within our lifetimes. Well, if we know how many people, and we know productivity per person, energy consumption per person, we know energy consumed every year under this scenario. Multiplying those 3 functions together brings us on to this top curve, so-called business as usual. Now, we can meet that demand no problem with coal. Every region of the world is increasing its amount of coal burning now relative to other fossil energy sources. And as China put up a mind-boggling 2 gigawatts of coal-fired electricity a week for every week last year, those plants are going to be up for the next 40 years because it's cheaper to tear them down than it is to do anything else with them. So we will be lucky to stay on that top curve. And there's no problem getting all the energy we need, except for one little problem. Here's historical data of the amount of carbon emitted per unit of energy produced, averaged over the energy mix of our planet. Now, we started with bad engineering by heating ourselves in caves. And when you heat yourself in a cave, most of the energy goes out of the cave and hardly any ends up to the end user. And so you emit a lot of CO2 from burning wood per unit of energy delivered. And then we got better. In the 1900s, we started to power our locomotives off of coal. And that wasn't bad engineering, that was just bad chemistry. Because coal, by mass, is all carbon, and when you burn it, you make all carbon dioxide. And you can't do anything about that number, because that number is a fundamental property of the heat of combustion of coal and its chemical formula. We got better and started to decarbonize on average our energy mix as we went toward lighter fossil fuels. Natural gas is less carbon intensive because when you burn one molecule of CH4, you make one molecule of CO2, but two molecules of water, H2O. So more of the energy gets released in producing water and less proportionately makes carbon dioxide. Oil is in between, roughly, because its chemical formula is in between. We were here in 1990, and the IPCC projected under business as usual that we would continue to decarbonize the energy mix for the next 50 years in accord with the historical trend globally. Now that easily tells you that the average energy consumption of carbon would be less than that of a pure natural gas economy within our lifetimes. Furthermore, to the extent that we don't kick the habit of oil and coal immediately starting today, and that we have roughly equal parts oil, coal, and gas, you need even more carbon-free power to get the average down to better than a pure natural gas economy. But we'll assume we do this too. So in addition to saving energy down to twice the level it takes to eat, we will assume that we continue to decarbonize the energy mix to better than a pure natural gas economy within our lifetimes. If we know the amount of energy consumed in every year, and we know the amount of carbon emitted per unit of energy consumed, it is just arithmetic to multiply the two together to calculate how much carbon dioxide will go into our atmosphere under that scenario. You can correct, of course, for the fact that only roughly half of what's emitted stays because the other half goes roughly in equal parts into the oceans and the biosphere. That correction has been made. And the significance of that is that brings us onto this top curve, the so-called business as usual curve. The significance of that is that even that scenario that I showed you is not even close to what it would take to hold the atmospheric levels of carbon dioxide at numbers as given by these curves in parts per million in the air. If you wanted to hold it at 350 parts per million, you have to follow this trajectory. That is, within our lifetimes, we can't emit a molecule of CO2 on our planet again forever. If you want to hold it at 550 parts per million, double what any human would have otherwise breathed, you still have to do better than that scenario that I just showed you. Many people now believe that no ice will exist in the northern hemisphere at less than 450 parts per million of CO2. We do not know, outside of a climate model, which, if any, of these levels are or are not, quote, safe. We just know what we see. What we see is that undoubtedly, no matter what you think of correlations versus causality, that CO2 levels in human history have never been above 300 parts per million and have been in a narrow range between 200 and 300. And that CO2 level variations of 100 parts per million have been repeatedly correlated with, but not necessarily proven to be the causes of temperature changes that have taken us in and out of glacial ice ages. We just know that within 50 years, we will bring it to a level that is double what any human will have otherwise experienced. And in essence, as a chemistry professor, I can tell you that we will just be doing the biggest chemistry experiment with our atmosphere that humans will have ever done. There's one other fact which I need to tell you, is that the people here understand, I'm sure, what happens to that CO2 that's in the air is that it is not chemically formed and destroyed like ozone. That means since there's no natural destruction mechanism of it, it has to be physically moved away. And after it's equilibrated with the near surface oceans, mixing through the thermocline is slow. And in fact, best estimates by Archer at the University of Chicago are that if we were to go to 200 to 550 parts per million and kick the habit, that 3/4 of that would decay with a 400 or 500 year time constant, and the other 1/4 would decay on a 10,000 year period, for an average lifetime to restore our atmosphere to where it is now of about 3,000 years. And nobody has a technically credible way of getting rid of the 600 trillion pounds of CO2 that will be well mixed in our air within our lifetimes. If you do, don't tell me, tell Richard Branson. He'll give you $25 million on the spot. No matter what the hypothesis is, we can say with best scientific knowledge that we are going to change the chemistry of our planet for a timescale comparable to modern human history. That's the problem. Under business as usual, embedded in that, to get that average carbon intensity down to better than a pure natural gas economy, assuming we save as much energy as twice what it takes to eat, you need almost 10 trillion watts of carbon-free power. If you want to hold it to double, you need more than that. If you want to stabilize it at 450 parts per million, you need more than that. By any measure, you need to bring on as much carbon-free power within our lifetimes as all the oil, coal, gas, and nuclear power on our planet today combined. And waiting 40 years to do this means you have 40 more years of emissions under your belt that simply do not go away. No matter how you slice it, if demand will double, you have to save as much energy as all the energy we consume today and make as much clean energy as all the energy we consume today if you want the arithmetic to work out. That's the challenge. That's why Marty Hoffert said, wait and see is wait and do. On the other hand, without policy incentives to overcome inertia in any non-authoritarian regime, how will we do this in time? And the parallel hypothesis is that this is more than just having political will to implement existing technology, that it's one thing to say we can fly to the moon, it's another thing to give with a gavel Southwest Airlines at LaGuardia telling them they can fly to the moon and expect that we go there every hour with them handing out peanuts along the way. Those are two different things. So now I want to turn to the technologies that could allow us to actually constructively deal with this issue if society chooses to do so. I haven't told you we would. I haven't told you we wouldn't. I have told you that I think we have at most 10 years to decide which path to take, because the Earth will take a path if we choose not to take a different one. The only proven technology that we have today that can scale to these levels is nuclear power. Now, I am personally not against or for nuclear power. But if we vote to do nothing else, this is the only card we have on the table. Fusion could be there in 35 years from the time you ask any fusion scientist of when it will work, is always 35 years from the question. And ITER is an important $10 billion experiment designed to work in 35 years, where working is defined as running for a week at full energy before the radiation and neutron flux will make that whole reactor have to be shut down and decommissioned. That's an entirely different thing than building a commercial system. So the short answer to fusion is time. We just don't have time in the first half of the 21st century to do that. We do have nuclear fission. I already told you that nuclear fission plants are built to confine that point source of heat and radiation at the levels at which the NRC will safely permit them for 50 years of operation. And they produce 1 billion watts. And I told you that if you cared about this problem, you had at minimum to produce 10 trillion watts, which means that unlike the 43 reactors we heard in our political campaign, the real cruel arithmetic of energy is that you need 10,000 nuclear reactors. That is, you need to build one every other day continuously somewhere in the world for the next 50 straight years. Nothing else is serious if this is what you care about solving as a problem, and this would only hold CO2 to double if we saved energy down to twice what it takes to eat. That's the scale of energy. There are a few problems with this. There's only a few terawatt years of terrestrial total uranium resources on our planet if used in once-through cycles. You could get it out of mining seawater, of which there is a lot more, but it's also at 3 parts per billion. And so to do this, you would have to have 3,000 Niagara Falls running in all the oceans of the world all the time to mine the necessary volume of uranium. Of course, you can do it with breeder reactors. It's the only proven way. So you would have to think about a world where we built a plutonium-containing nuclear reactor in every country that needed energy starting today. We should credit North Korea and Iran for stepping up to do their part to mitigate global warming. If you only build, oh, by the way, the recent Florida Power and Light study, when showing the next nuclear power plant in the United States, what it might cost came in at $5 a watt, which amortized out at between 12 and 15 cents a kilowatt hour. So if you wanted to do this with economy of scale, you might get it down to $50 trillion, which used to sound like a lot of money. If you only build a nuclear reactor a week, you'll leave 90% or more of the problem on the table. So then we need to turn to utilizing the other two possibilities, which is one, cleaning up the existing fossil energy through carbon capture and storage, or sequestration. Formerly, probably until recently, and still now until revised, our nation's #1 clean energy policy. But clean coal is an oxymoron except on television until you prove you can actually capture the CO2 with integrity at scale, which nobody has ever proven. You could put it in the deep oceans. There's a lot of volume there, but people are worried about changing the pH in the ecosystems. You could put it in the oil and gas fields, which is where the oil companies want to do this first, because of course, natural gas having been trapped for geologic time, the CO2 will probably stay there also. But there's only 30 or so years worth of total global capacity in all the geologic reservoirs. And don't be fooled, the only proven way to enhance oil recovery is to pump CO2 down into the ground so you make more oil coming up than the CO2 you capture. The only place there's enough volume is in the underground aquifers in the brine, where optimistic estimates say there's 150 years, pessimistic say there's 50 years worth of global capacity. And we won't know for sure until we try to do it. The good news is when you dump CO2 down into brine, you make Perrier. Perrier costs more per gallon than gasoline, so we could export it to the French. The bad news is the stuff can't leak. I already told you the lifetime of CO2 in the atmosphere is a few thousand years, which means if you're putting this stuff down there at 1 billion tons a year, it can't leak. If it leaks at 1% a year, after 100 years, the net flux is the same as what you tried to mitigate in the first place. So a technically credible version of, quote, clean coal would mean understanding the fate and transport of CO2 underground, that the global average leak rate is less than 0.1% a year for 1,000 years. And we have to know that within the next 10 years. We know CO2 comes out underground. In 1985, it came up and killed 2,700 people in Lake Cameroon. You can see it in Mammoth Mountain here, where it's coming up out of the ground. It is buoyant under the ground. By the way, one of the final options in future gen in the United States where we wanted to site it was in Texas. There are 1.5 million holes in Texas in the rock from oil drilling, so there are a lot of fingers to plug up your dike in if that's where you want to put it. We should absolutely, in my opinion, be doing everything we can to demonstrate that we can understand the chemistry and science behind the fate, transport, and modeling of CO2 at scale below the ground. We should absolutely, in my opinion, not be blindly going ahead, counting on putting it all there, hoping that in 10 years we don't find that it's come up and hurt somebody. You can imagine if one of these reservoirs leaks that in the meantime someone will have sold carbon credits on the secondary market, bundled together with other carbon credits, and we've seen how that movie ends. That's clean coal. It should be pursued vigorously, but a rational portfolio would not count on it. Which brings us, if you don't just do more than build a nuclear power plant a week, and even optimistically clean up 1 gigaton per year of emissions from coal-fired power plants, as the only other trump card you have left is renewables. And there are 6 major renewables: hydroelectric, geothermal, wind, oceans, dear to our hearts here, biomass, and solar. I won't go into the full details here, but I will just give you some of the summary results, and I'm more than happy if you want to refer to my website or talk to me in detail about the actual numbers behind all of this. So hydroelectricity is a model renewable energy source. It's true when you build a dam in China, you only displace 1 million people, but every renewable energy source has its problems, like all energy sources do. Hydroelectricity's big problem is it's cheap, and so we've already done it pretty much everywhere we can do it. In fact, you can know the potential energy of all the rivers, lakes, and dams and all the water flow on our planet combined. And the geologic potential is 4.6 terawatts. Now, you can't dam up the Okefenokee Swamp and get much energy out of it. So where you can technically do it, you can get 1.5 terawatts. You could technically dam up the Hudson River, but the Yankees would have to find yet another place to play. We already have their manager in LA. Too much stress on that. So where you can economically do it, it's been estimated to be 0.9 terawatts, and we've already installed 0.6 globally. There's no room to grow. Just forget about it. What about geothermal energy? We know the temperature of the core of the Earth. We know the temperature at the surface of the Earth. We know the thermal conductivity of the Earth. Any geophysics textbook tells you in the first chapter that the sustainable geothermal heat flux to the surface is 57 milliwatts per square meter. Well, if you forget to salute to that French sergeant named Carnot and assume we'll build 100% efficient heat engines and cover all land on Earth, you would get 11 terawatts. Now, there's proposals to drill deeply to 10 kilometers in order to get more heat. That's unsustainable. It's like cutting down trees at a faster rate than they can be regrown. This is the sustainable heat flux. There's no doubt you can drill down further and get more heat, but you have to remember when you drill down deeper than almost the deepest oil wells, what you would be getting would be steam, and the energy density of steam in a good geothermal well pair is 5 megawatts. And for comparison, the energy density in a Saudi oil well is 500 megawatts. So the proposal would be involved in drilling ultra-deep wells that would be on a scale 100 times greater than our existing oil and gas industry for something that had 1/100th the energy content, which you can decide if it sounds worthwhile or not as an option. You can look at wind. Wind is somewhat controversial, Best scientific estimates are, say, the practically extractable amount of wind in all the windy areas on land on our planet combined is a few terawatts, 2 to 3. Now, there is one number by Archer and Jacobson at Stanford where they took the point source wind measurements and then multiplied by all the area on Earth and got 72 terawatts out. But you can't do that because I know as a windsurfer that when I get behind a sailboat, it takes my wind away. And the same thing happens for wind farms when they would be deployed on a scale length comparable to the mixing and scale height in the atmosphere. And so you can't just take the point source data and multiply by arbitrarily large areas and count all the energy over and over again. So best estimates are a few terawatts. We should be using wind where we can, where it's economical. It's the fastest growing renewable. But don't look for it to fill this gap in any significant way other than a 10 or 20% of our electricity, which I already told you was only 10% of our energy. Here's a 20 terawatt line. Here's all the energy in all the ocean currents, in all the tides, in all the waves on our planet combined is not even close. We hear a lot about biomass, but plants are a fundamentally inefficient machine at converting energy. If you take the fastest growing plant and you take over the year all the energy produced in all the biomass and divide it by all the energy of the sun that hit that acre in a year, it's less than 1% of the total energy that hit it that's stored. And the reason for that is that nature protected plants against bright sunlight and against CO2 fluctuations, and so they saturate in their productivity at 1/10 the light intensity of the sun to prevent themselves from undergoing more radical damage than they already do. They already rebuild their machinery every 30 minutes in photosynthesis, and a large amount of the energy budget in the plant is used just to keep it going. Yes, in universities we know that as overhead. Plants have the same problem. If you took all the land on Earth, well here, let's just do it this way. You take all the land you could grow crops. You take the land we currently use to grow crops to feed us, you take half again as much to feed twice as many people, take all the rest, plant the fastest growing known switchgrass on all of it, assume no energy into the farm and no energy needed to do the farming and burn it all at 100% efficiency, and you might get 5 terawatts. Now that doesn't count the fact that when you tilled the soil, you incurred a carbon debt when you changed from one crop to another, and the amount of carbon released to the air has to be paid back, and the amount of carbon in the soil is about twice as high as the amount in the entire atmospheric column above it. And to pay back that carbon debt takes between 40 and 400 years, depending on the crop switching you did. And so from a net CO2 offset level, best estimates are now you need to discount this value by another factor of a few. Biofuels could be an important component of our energy mix because this is an important terawatt or two. Because if you have to cut emissions down that much, nobody in my mind yet has figured out how to make a plug-in hybrid airplane fly. And so we're going to need liquid fuels for aircraft transportation, for ship transportation, which is almost 40% of total transportation. So we need to focus on the whole system, not just an obsession with light-duty vehicles. By the way, if you care about this, last year 30% of our corn provided 2% of our transportation fuel. And yes, we have a law in Congress that says we have to do 5 times more than this by 2020. Quick math tells you there's a little problem. The reason plants can be significant is that even though they're inefficient, they use the biggest energy source that we have, which is the sun. The sun provides us with 120,000 terawatts. More energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Nothing else comes close. So if you want to play these cards, it's pretty obvious where the big market here is It's trying to get about 10 out of that 120,000. Photosynthesis on our planet right now produces 90 terawatts. So we know it can be done. Here's a map. This is a pretty famous map of mine now. If you had a 10% efficient, not like plants, 0.2% efficient farm, this is the amount of land you'd have to cover to power the whole energy of the United States forever. The good news is there are a lot of clean, green jobs. This little county in Kansas would be a member of OPEC. They would like that. The bad news is it's not a small area. It's bigger than 10 times everybody's roof. It's comparable to our nation's numbered highway system. The good news is I've given this talk now for 5 years to over 100,000 people, and I've never met anybody that actually lived there. Just not gonna miss it. Here's 6 3-terawatt boxes. There are only 2 problems. Problem 1, solar cells cost way too much money. And you cannot get from here to there by just increasing their efficiency. You have to really lower their costs. You have to lower their cost by a factor of 5 or 10 because we know the energy of the sun, and if you only get 10% of it, then I know how much I have to sell you that energy for 20 years to pay back just what it cost me in the first place. The other point is, to be fair, if you have to build a nuclear power plant every day, you have to put up 1 million solar roofs every day to make the same amount of power. We in California have a goal of putting up 1 million solar roofs in 10 years. If this is the problem you care about, we would have to put up 1 million a day in our country every single day starting today. That's what a serious effort is. We don't make enough silicon to even think about doing that, enough people on roofs to think about doing that. So we need a way to make this like carpet or make it like paint that you can roll out or buy from Home Depot. That's a disruptive technology that would really change our ability to get to scale. And there's one other little problem. The other little problem is sun has this nasty little habit. It goes out locally every single night. And if Johnny Cochran were giving this talk, he would say, "He that cannot store shall not have power after 4." You cannot build an energy system around an intermittent source without storage. And there is no mass cost-effective way to store quantities of electricity at scale. If there were, you should buy it every night at a nickel a kilowatt hour and sell it to everybody else in the room the next day at 25 cents a kilowatt hour and laugh all the way to the bank. The cheapest way to do that now is to pump water uphill, which is fine every winter and emptying it every summer, but not every day and every night for the whole United States. To think about the difference in energy density, if you want to store the energy in 1 gallon of gasoline, you would have to pump 55,000 gallons of water up the height of Hoover Dam. That's the difference between the chemical bond energy and the gravitational force on a mass. I think the only way we could get to scale in energy storage is what nature already figured out, which is in chemical bonds. The only thing that beats it is the nucleus in the atom. So we have to find a way to store sunlight in chemical bonds in order to make the volume of storage compatible with things that we as humans can assimilate and understand. We could do this today, perfect. If we wanted to, here's our hydrogen economy. We could take this parabolic dual-axis trough, focus sunlight onto this external Stirling engine. We could put that electricity into this electrolysis unit, which probably has half the world's supply of platinum. And every day, this plus this would fill up that tank with hydrogen. And you would have to build one of these every second for 50 straight years. This is why what we have is not a scalable technology. This is why we need R&D to continue not only to do what we know how to do now, but to do the things we don't know how to do now so we can get from here to there. If the amount of platinum in a fuel cell needed to power a school bus costs $500,000 like it does today, then we will have a vigorous hydrogen economy consisting of stolen school buses. the driver is going to say, see ya, right? We know this can be done because we know there are bugs that do it. We know nature has hydrogenases that don't use platinum, they use iron. They're not poisoned by carbon monoxide and sulfur, they're in the molecule for function. We just need to be able to do it ourselves, which will only come through people not building demonstration systems and deploying what we have now, but in addition, doing R&D to understand how to make the next generation of energy technology in the 10 years that we have to do it. So finally, we're going to need additional energy. There's never been a year in the world where we've used less energy than the year before. You know, we talked about Kyoto, and here's what talk did. CO2 emissions grew at 1.1% between 1990 and 1999, and then we tightened up our belts and showed the world what we could do, and we tripled it. And now they're growing at 3.1% per year. So that scenario I showed you, business as usual, is in our rear view mirrors already. You don't have a chance without energy efficiency of making a hard problem just seem impossible. And we should be doing everything we can to meet that goal embedded in business as usual of getting energy down to twice the level it takes to eat. But no amount of energy saving ever put food on somebody's table. No amount of saving energy ever turned on a light bulb. You still have to make massive quantities of clean energy within our lifetimes if this is a problem you care about solving. The only three big cards we have are carbon capture and storage, if we can prove it works technically, our nuclear reactors with full fuel cycles, if we want to embark upon the safety and proliferation issues associated with that at scale, and or in some combination using the biggest resource that we have, the sun, but it's got to be really cheap and it's got to make a full energy system which involves storage so that we can get power to wherever it's needed, whenever people want it. That's what a sound energy policy would really involve as its trump cards, in my opinion. Energy is very polarized. This will cost money. At one extreme, policymakers say this is something we can't afford to do. At the other extreme, remember, CO2 lasts for thousands of years, so this is something at which perhaps we can't afford to fail because we are the only people that has come to this place in the road and get to decide which path our planet will take. So with that, thanks so much for listening, and we'll move on.